In this video, we're going to talk about Lewis dot diagrams, and in doing so, we remove the D block and the F block because we're only concerned with the S and the P block, which are the two representative element columns. So we're going to number them 1, 2, skip the middle, 3, 4, 5, 6, 7, and then I'm going to put an outline around helium because helium is an exception. Helium has 2 valence electrons, but everybody below it has 8. Helium's exception is called the duet rule. And because helium's electron configuration is simply 1s2, then it will have a maximum of 2, as opposed to, say, neon, which would end in 2s2, 2p6, and the sum of 2 and 6 is 8. Lewis dot diagrams take the number of valence electrons, which does correspond to the tall group, or the tall family that it's in, and puts them around the symbol for that element as a dot. We don't represent every electron in a Lewis dot diagram. We only represent the valence electrons because those are the ones that you can consider to be the most important in chemical reactivity. Hydrogen is in the first family, which means it has 1 valence electron, so you would put simply 1 dot around the outside of its symbol. Although helium is above the noble gases and every other noble gas has 8, remember that helium has 2, and those 2 will be paired up on the same side of the symbol. Lithium also has just 1 valence electron. It would be symbol, and the symbol would look like this. Both beryllium and helium have 2 valent electrons, but the way that you would represent the valence electrons in beryllium is different than helium. In general, you would spread them out on either side. You may see those 2 electrons on beryllium paired together like helium, but I believe personally that it's best practice to spread out electrons when they are not helium. And you'll learn more about why that is helpful when you do Lewis structures. But for the most part, you can roughly think of those unpaired electrons, those 2 electrons for the Be in the Lewis structure, as available to make a bond. As we pick up in the P block, you can see that boron is in the 3rd tall column, so it should have 3 dots. The way you would arrange those 3 dots ideally is start anywhere you want, but spread them out. Carbon will also be spread out in this way. Every edge, top, bottom, left, and right, can hold up to 2 dots. Now nitrogen has 5 dots, or 5 valence electrons, that need to go on the diagram. To put them on, start anywhere you want. I tend to start at the top, even though I didn't start at the top for the last 2. When there are more than 4, I usually start at the top, and I would make it like this. To put 5 on 4 available edges, and by edge, I mean top, left, bottom, or sorry, top, right, bottom, and left. Those are edges. There are 4 available edges for any symbol, and I will tend to put them starting at the top. 1, 2, 3, 4, 5. In this way, it is somewhat similar. Not exactly, so don't get this too deep into your head, but it's somewhat similar to Hund's rule with electron configurations, where you spread them out as much as possible and then you go back around. Oxygen has 6 dots, or 6 valence electrons for its Lewis structure. Starting at the top, it would be 1, 2, 3, 4. Now at this point you can pause, and there is no right or wrong way to do this, but to put the 5th and the 6th one, you can put them here and here, or you can put them here and here, or you can put them here and here. There's no right or wrong way, so long as you don't do this. Now for oxygen, there are 6 valence electrons, but you do not want to leave one edge free. They will not pair up first. They should be spread out. And the reason for this, as you'll learn, like I said earlier, when you get to those Lewis structures, is because oxygen will want to make a bond with that available spot and this available spot, or wherever you have those two unpaired ones in your Lewis structure. We'll end with 3 more examples. Calcium is in the second tall column, or it's in the second family, so it will have 2, and it's best if they're spread out. However, if they're together, as you will see sometimes, it's not the end of the world for that particular family. Chlorine would have 7, so spreading them out as you would expect, it's 1, 2, 3, 4, and then go back around again, 5, 6, 7. That single electron can go anywhere on any edge. It can go top, bottom, left, or right. You could rotate those 2 and 1 around. Doesn't matter as long as you have one free area. Some people, as I try to do when I'm doing this, will keep the single electron on the right, but it does not matter at all. For phosphorus, phosphorus is in the same family as nitrogen, so it will follow the same rules. 5, 1, 2, 3, 4, 5. Please remember that this one that I just drew is the correct way to do phosphorus. The incorrect way that some people may show you would be this one. So I'm doing it in red. Phosphorus incorrectly would be this way. Just remember to spread them all out if you have 4 or more. We're going to do some quick practice with drawing Lewis structures for molecules, both the dot and the line form. I will tell you now that this is important. Each line in a Lewis structure represents a bond, and that bond itself represents 2 shared electrons. For Lewis structures, you may have to erase and redraw to refine your structure and make it more appropriate. As a general rule, the first atom is the central atom, though not always. Sometimes you'll have to be told, and it just comes with practice. However, if the first atom is hydrogen, then it is not the central atom. Hydrogen can never be the central atom. Outside atoms are everything such as hydrogen and the halogens, and then oxygen is usually an outside atom, but it depends. As I said, it does take some practice and exposure to these structures. For methane, the first thing you do when you draw a Lewis structure is count up all the valence electrons. Carbon has 4 valence electrons, and hydrogen has 1, but there are 4 hydrogens, so that gives me a total of 8 valence electrons. My first atom is not hydrogen, it's a carbon, which means it does go in the center. So C might go here. I'll move that to a different location, make it more spatial. I'll put C here. Now, with carbon in the middle, I'm going to draw carbon's electron dot diagram, or its Lewis structure. We know that carbon would have 1 on every edge. There are 4 hydrogens. Now the hydrogens will go all around the carbons. Hydrogen also has 1 valence electron, which you can put here. To represent methane, you can recognize that every 2 electrons that are shared, where 1 comes from one and 1 comes from another, it's called a covalent bond. So the way you could redraw this is carbon sharing electrons with 4 different hydrogens. This is the Lewis structure with lines on the right, and on the left is the Lewis structure with dots. And the Lewis structure with dots is simply a combination of the Lewis dot diagram for the elements that are present. To count water's valence electrons, it's the same process as for methane. There are 2 hydrogens, and each hydrogen has 1. And then you're adding to that the 6 from oxygen, giving me also 8 valence electrons in total for water. So water structure will look like this. The central atom is oxygen. So I'm going to put oxygen in orange. And we know that oxygen has 6 valence electrons. The way that I spread them out is 1, 2, 3, 4, 5, and then the 6th one can go wherever so long as you create a pair. I'm going to put them here. Put it right there. Hydrogen will go where there's a free spot available. And when I say free spot, I'm really talking about an unpaired electron on the Lewis structure for oxygen to make this water molecule. Now I'm going to put it right here. Remember that the purpose for the Lewis structure is to show you what the molecule will look like. In general, molecules or atoms are most stable when they have 8 valence electrons, with the exception of hydrogen, which is 2. So let's check for each. This oxygen here has 8, which is what it would be most stable with. Hydrogen here has 2. And remember that hydrogen and helium are fine with 2. And this hydrogen also has 2. Now they only got their full outer shells by sharing electrons in the molecule. Recall from the rule at the top that when electrons are shared, when there's one electron from one atom and one electron from another atom, then they can become a bond. So this and this are going to become a bond, and I'll show you what that looks like. Rather than drawing those dots, you can draw them as a bond. And you are familiar with water looking like this. We're not getting into the third-dimensional structure of it right now. That comes up in something called Vesper theory. But in the future, you'll learn that water is bent and it's not linear. Right now, it looks like a line. In reality, those two lone pairs should be on the same side of the molecule. In drawing ammonia, we're going to do the same thing we did. We're going to count our valence electrons. Nitrogen has 5, and each of the 3 hydrogens has 1, totaling also 8 valence electrons. Nitrogen is in the middle, and it has 5 valence electrons as we saw, so it will be spread out on every edge like this. There are 3 hydrogens, each with 1. Now if you look at nitrogen's Lewis dot structure, or Lewis dot diagram, there are 3 areas that can be open, so to speak, to accept another electron. There's an area here, here, and here. Because of that, hydrogen will come in with its single electron and put it in the spot available, so to speak, where nitrogen has an unpaired electron in its Lewis dot structure. And as we said, those shared areas here, here, and here are really just bonds. They're covalent bonds in this case, and you can represent them as lines. Remember that each line represents 2 dots, which are electrons being shared. These electrons on the edge right here, you cannot represent as lines, or really you shouldn't, because I think it's tacky. But these electrons here are something called lone pair. A lone pair of electrons are 2 electrons on the edge of one particular atom in a molecule, or on the edge, like an outside atom or an inside atom, and they are not bonded. They are not bonded, they are not shared. So there are a pair of electrons that are not shared. Now that we know the term for lone pair, we can see that a methane molecule has no lone pair, and a water molecule has 2 lone pair. Both of the lone pair are actually on the are on the oxygen molecule, or the oxygen atom in the water molecule.